Exponents rules. Okay. So this is our week 9 workshop. Originally, this said just exponent rules practice, but we've done enough of sequences and series that we can do some practice with the easier questions there. Just kind of basics and general skills of sequence, and then arithmetic sequences and series. But still the easier version, geometric sequences and series is the more, not that much harder, but the more deeper, kind of the more interesting version, which we will be getting to next week. This is the list of questions that I have. So some exponents review questions here, these 4, and then there are actually a bunch in these are 5 total. Then just identifying some sequences here, and then using our formulas that we saw in today's class or yesterday's class, depending on your section, for arithmetic sequences and series. Okay, let's jump into these and get to them. So exponents, first, just all of these questions for exponents will just be about simplifying. So take a moment. Shouldn't, both of these here should not take too long. You can type your answer into the chat when you have it. Maybe 1 minute max to work. Go ahead. Okay, let's take a look. So the one on the left, first we'll take kind of this thing and this thing. What's the rule that we have here that would let me simplify each of these separately?
First, we have to multiply the powers, the exponents of the first
part of this. So if we have an exponent to another exponent, 2a to the exponent 2, a squared, then again to the exponent 6, we multiply the 2 exponents. So that's a to the exponent 12 times a over here, same thing, to the exponent 24. Okay, then now we have 2 things here. We have different exponents, but we have the same base, and the bases are being multiplied together. What can we do?
We'll add the exponents.
All right, add the exponents. So just 12 plus 24, 36. Done. For the one on the right, we have the same thing, just with kind of a lot of different parts here. So we'll take the thing on the outside, this exponent on the outside, and we are going to apply that exponent to 1, 2, 3 things on the inside here, sort of the, not factoring, it's the reverse of factoring, like expanding. So get rid of the brackets here. So we'll have -2 exponent 4a, put this in brackets as well, a to the exponent 3a cubed to the exponent 4, and then all that also times b squared to the exponent 4. Each of these will use the exponent rule that we had on the other side here. So that's a to the exponent 12 times b to the exponent 8. And then here, -2 to the exponent 4.
16.
Okay, positive or negative?
Positive.
Positive 16. What we could have done here, instead of -2 to the exponent 4, we could think of this as -1 to the exponent 4 and also 2. Just positive 2 to the exponent 4. So that would be 16, and then -1 times itself 2 times would be positive, 3 times would be negative again, 4 times positive again, like that. But the result here will just be +1. All right, so positive 16 times 8 to the exponent 12 times b to the exponent 8.
Professor,
Yes?
I didn't understand -2 exponents 4.
Which part?
How did the result come 16? You multiply 4 in 4 or multiply 2 4 times?
It's an exponent, so it's -2 to the exponent 4 is equal to -2 times -2 times -2 times -2. -2 times -2, 4 times -2 times -2. And that's 4 times -2 is -8 times -2, and the last one, 16. So it's an exponent. We are not multiplying 2 and 4. It's -2 times itself 4 times. Any other question? Nope. Okay. Next ones. Take a moment and try to solve. Okay, let's try to solve these. So the one on the left, let's take each of them separately first, but then we see, okay, there's an M on both sides, there's an N on both sides. We're gonna have to combine these at the end here, but for now, let's keep them separately. So again, just like expanding, we're gonna take the 2, not the 2, the square, exponent 2 on the outside, and we are applying it to each of the things on the inside. There are 1, 2, 3 parts on the inside here. So 3, put our brackets here, 3 squared, 9. M squared, then squared again. So that's m to the exponent 2, then again to the exponent 2. So exponent to exponent, we are multiplying those 2 times 2. So m to the exponent 4. What is our n term here?
2.
2. It's a square because we understand that there's a little 1, there's an exponent 1 on the n here. So we don't write that, but we know that it's there. 1 times 2, so n squared. All right, and then the other one, we have 2 to the exponent 4. That's 16. We have m to the exponent 1, then times 4, because we have this other exponent. Total is 4 there, and then n, 5 and 4, multiply them together, give us 20. Okay, so there's the left, there's the right, and now we're just going to combine the two sides here. 9 times 16, 144. 9 times 15, yeah, that's right. M4, so that's m to the exponent 8, and then n squared, n to the exponent 20, so n to the exponent 22. Simplified. All right, our next one here on the left. What's the first thing that you would do here?
Calculate the g minus 2 plus g minus 5.
Okay,
Right.
so the top of the fraction inside the brackets here. So j to the exponent -2, j to the exponent 5. What are we doing with the exponents to simplify that?
It will be 3 as we're calculating them, simplifying them.
So we're just adding the two together. We have the same base and the bases are being multiplied. We understand there's a little multiplication dot in between. So -2 plus 5, 3. And then on the bottom, j exponent 4. And all that's cubed. What's the next thing we do?
Simplify the expression.
Yes, that's the whole thing. Which part of the expression?
In the brackets.
In the brackets. Okay, so our fraction here, j over j cubed over j to the exponent 4. How can we simplify that?
We have to raise to the exponent 3. J cubed is raised to the exponent 3, and then over j to the exponent 4 is raised to the exponent 3.
Okay, so we could do our expanding. We could bring this 3 in and apply it to the top and the bottom. We don't need to do that now. I think there's a slightly simpler thing we could do first.
We can simplify j3 to j4. It will be 1 and g only g.
J to the exponent what?
No, it will be 1 and delete j, kind of.
-1.
Okay, so let's write out what's happening here. J to the exponent 3 over j to the exponent 4. What we are simplifying this to is we have the same base, j, but we have division here. So when we did it on the right, sorry, on the left side here, and we are multiplying the two, then we add the exponents. But if we are dividing, then we subtract the exponents. So it's j to the exponent 3 minus 4. And that turns into j to the exponent -1. So this simplifies here, j to the exponent -1 cubed. Okay, so now we could have taken our cubed and brought that in at any points, but the number, we would get the same result, but the numbers are just a little bigger. This is a bit simpler. So -1 times 3 means j to the exponent -3. And by convention, what's the last thing we do to kind of make this look a little nicer?
1 over j cubed.
1 over j cubed, like that. So we get rid of the negative sign in the exponent by turning it into like a 1 over whatever. Okay. Oh. These questions. Any questions about these ones? Okay, so lots of different exponent rules to remember, and they all kind of get used a lot. So just remember with the multiplying, like with the m4, maybe this is easier example, n squared and n to the exponent 20 here became this. So it's the same thing here, except instead of multiplying, we're dividing. So instead of adding, we are subtracting the two. But it's underlying, it's the exact same like principle and rules, just the adding changes to subtracting, multiplying, changing to dividing. All right, let's go to the next set with rational exponents, so fractional exponents. That's what this means. So things like this. So we can definitely have exponents with that are a fraction. Let's just okay, let's do A here together. We'll talk about what it would simplify to, and then I'll let you do the next two, just to make sure everyone remembers here. So just like we had before, same base, C and C, and they're being multiplied together. So we add the two exponents. So this is equal to C to the exponent 1 over 4 plus 5 over 8. So the 1 over 4 plus 5 over 8, the whole thing is inside the exponent. If we add those together, what do we get? One over 4 plus 5 over 8.
I get C to the exponent of 7 over 8.
7 over 8. So it's 2 over 8 plus 5 over 8, 7 over 8. Okay. If we have a fractional exponent like this, then what? How can I rewrite this using a root of some kind?
8th root of C7.
8th root of C. And where's the 7 going to go? On the inside or outside of the root?
Inside.
Inside, okay. So that's one way. Or the other way of writing it would be the same thing. 8th root of C with the 7 on the outside, exponent 7 on the outside. So it doesn't matter, it's the exact same math, but in different situations, thinking about it one way or the other way might be a little easier for you. Okay, so here,
Professor,
yeah,
C7 over 8. How did you bring this?
from here,
Yes, how?
1 over 4 plus 5 over 8. If we are adding fractions, we make the denominators, the bottom numbers, the same. So 2 over 8 plus 5 over 8, and then we add the top numbers, 7 over 8.
Thank you.
You're welcome. Okay. So B and C, take a moment now and try to simplify those. In this case, you don't need to do this root thing here. You can just leave it as a fractional exponent, but simplify the fractional exponent. Go ahead. Okay, let's try to solve these. So one in the middle here. So we're taking the exponent to an exponent. So we take the exponent on the outside, multiply it by the exponent on the inside. So that's p to the exponents, 12 times 3 over 4. 12 times 3 over 4. So what is 3/4 of 12? Or we could be rewriting this as 36 over 4 and then simplify the fraction. And we will get p to the exponent 9. So just multiply the two numbers together. The one on the right here. What's the first thing we would do? What's our first line?
R exponent 4 over 5 minus 9 over 5.
Okay, so we are dividing here. We have the same base, R and R, and we are dividing. So that means we are going to subtract the fractions from one another. So that's R, all, and then to the exponents, all of this in the exponent, 4 over 5 minus 9 over 5. What's the result of that?
Rx to the exponent of -1.
-1. So 4 minus 5 is -5. So -5 over 5, that's -1. And then if we do our simplifying thing here, just 1 over R. A little exponent 1 there, but we don't need to write it. Okay, so even if we have fractional exponents like this, just we can add them or sometimes multiply them, sometimes add them, sometimes subtract them, and hopefully they'll simplify and kind of go away for us. All right, one more set of these exponent questions. Just give people a moment if they're writing. Okay. Last set of exponent questions. I'm not going to say anything, just go ahead, try to simplify. Okay, let's take a look at these. So the one on the left here, we have an exponent on the outside, just like our other expanding examples. We have two things on the inside, so apply the exponents to both of them. So 27, we don't need brackets here. 27 to the exponent 4/3, and then also q to the exponent 3/2, that to the exponent 4/3. Okay, let's do the q part first. That seems a little easier. So it's q to the exponent 3/2 times 4/3. And we're just going to multiply those together. We'll fill in the 27 part in a little bit. So q to the exponent 12/6. And then that's just 2. So q squared. Okay, let's do the 27 part of this. What can we notice about this? 27 to the exponent 4/3. What's the first thing we can notice?
Just cube root 27 first, and then the result, yeah, the exponent of 4.
Okay, so we kind of notice we have this 4/3. That's of course 4 and 1/3. 27 to the exponent 4. We probably don't know that right off the top of our heads. That sounds hard to calculate, but cube root of 27, 1/3 here. So cube root 27. Hopefully we recognize that number. That's 3
9.
cubed. Not 9, it's 3 cubed. So 3 times 3
81.
times 3. Okay, I'll get to our solution. Just hold on a moment. So this part here first, cube root of 27. So if we do that, then that's 3 to the exponent 4. Okay, and then that we can calculate. So 3 to the exponent 4, that's 3, 9, 27, and then just one more, 27 times 3. We might know that number. It's going to be 81. So 81 q squared is our final result here. Okay, so if you have an actual number, a constant with these exponents or roots, just, especially a textbook question like this, there's probably some root or something that's kind of convenient and that you could calculate easily. If not, you probably just leave the constant as is. Like if this was 26 to the exponent 4/3, that's not a clean number. We could just leave it like that, probably. That'd be much smaller. Or a simpler way of writing it. All right, one on the right here. 2 parts on the outside, sorry, 2 parts on the inside. Each of those will have the thing on the outside applied to it. So what's our next line for this part?
Multiply 1/3 by 3/2 and 2/3 by 3/2.
Okay, so a to the exponent 1/3 times 3/2, and b exponent 2/3 times 3/2. Okay, and we just simplify a 3 times 1, 3/2, a exponent 3/6, and b exponents, that's just, well, 6/6. So a to the exponent 1/2 and b to the exponent 1, just like that. So that's We could write this as square root of a times b. By convention, we'd often put the square root kind of second. So b root a like this, but doesn't really matter that much. At this point, we've solved the question. The other parts are just maybe we want to present the answer a little differently. But by that part, a to the exponent 1 over 2 times b, that's simplified. Okay, I always want to go on quickly, but I'll just give a moment for people to write. Just right now, I'm looking in the participants list. There's someone named iPhone. So if you want the attendance credits for this on the My SolBridge page, you got to rename yourself so we know who you are. Okay, going to move on. So the next part, sequences and series, or well, this part just sequences and kind of recognizing sequences and trying to figure out what the general term could be for a particular sequence. And then the next part we'll look at using the formulas for arithmetic sequences and series in particular. Okay, so let's start off here with these two. Just take a moment, try to write out the first 5 terms of each of these two sequences. All right, let's try these. So the one on the left, can someone tell me what is our first term?
4.
4. So we just, again, to evaluate these, we just put in the numbers there. A1 then is equal, just using this, 3 times 1 plus 1. That's 4. So first term is 4. Okay, tell me the next 4 terms.
7, 10, 13,
One more.
16.
16. So there we go. Just the difference here, or you tell me, what is the difference between each of these terms?
3.
3. So 3, 3, 3, 3. So this is an arithmetic sequence. We don't need to know that to be able to, write out the first 5 terms like this, but we can notice it's a common difference between all the terms. So does turn out to be an arithmetic sequence. The one on the right here, tell me what the first 5 terms are.
-2, 4, -6, 8, -10.
6, 8, -10. Okay, I'll talk just a tiny bit more about this one. So A1, we just have these 2 parts we would calculate. -1 to the exponent 1 times 2 to the exponent, or 2 times 1. So that's here, -1 to the exponent 1, that's just -1 and times 2. And of course, that turns into -2. A 2 here is -1 squared times 2 times 2. So that's a 4. And -1 squared, a negative number squared will turn into a positive number. So that's a +1 here. And then if we do a 3, -1 exponent 3, 2 times 3. So that's a 6. But then the -1 part, that will be actually -1 because it's -1 to the exponent 3. So -1 times -1 is positive, but then times one more -1 will become negative again. So that's how we are getting this pattern of negative, positive, negative, positive, negative, like this. What is the difference between each of these terms?
2.
Between -2 and 4.
6.
That's 6. What's the difference between the next two?
8. Oh, no. 10.
Let's get our direction. +10 or -10?
-10.
-10. The next two.
+14.
14. Okay. And then the next one, -18, like this. So is this an arithmetic sequence?
It's not.
It's not, because we have a difference. We do not have a common difference each time. If we didn't have the -1 part, then yes, it would be. But we do have it, so it is not an arithmetic sequence. So those formulas are not going to work for this one. One more thing I will say about this one. I mentioned this in one of the sections, but not the other two, so I want to say it for all of them. Let's say if I wanted the same kind of thing, except I want +2, -4, +6, -8, +10, etc. What thing could I change to build this sequence instead?
The second 2 multiplied with 2n should be negative.
That would work. Actually, that would work. There's a more kind of standard or cleaner way of doing it. Let's say our 2n is giving us the 2, 4, 6, 8, 10. I don't want to touch that part.
How about we change the exponent of -1 to n-1?
Okay, or n+1. Yeah, usually it is n+1. So n+1 times 2n would give us this sequence here. So this is a common way of handling this. If you want sort of negative, positive, sort of kind of flip-flop pattern like that, then either -1 to the exponent n or -1 exponent n+1, just depending on which thing you want to start off. If you want it to start positive or start negative. So this is, my camera went out of focus for a second. So this is a very common way of doing this, and it's a useful thing to kind of remember. -1 to the exponent n or n+1 gives you this back and forth kind of pattern. We see that a lot in sequences. Okay, let's go to the next ones. Right, one more of these with just general sequences, and then we'll go to the arithmetic ones. Okay, let's do the first one here on the far left. We'll do this together, and then I'll let you try the other two. we want to find a general term. So an equals something that will give us this sequence here. Does anyone have an idea of what we could do?
E exponent n plus 2.
E to the exponent n plus 2. Okay, so that seems like a good guess. How can we confirm, or how can we check if we have this right?
Just substitute 1 until 5 to the equation.
Okay, so we'll just try a few. The sequence is telling us A1 is this, A3 is this, A4 is this, etc. So just let's use our general term and calculate a few of those and see if we got it right or not. So A1 would be equal to E to the exponents n plus 2, and n is 1 here, so 1 plus 2. So yes, E cubed. That's right. Don't just check one of them. 2 is good. 3 is just a good habit. Make sure you, with just 2 of them, there are definitely mistakes that you could make where it would still be true for 2 of them. But so testing 3 is the way to really be certain. So A4 would be E to the exponent 4 plus 2. 4 plus 2, E6. Yes, that's what the fourth one was. Let's check another one. I know this is a pretty simple one here, but just building good habits. E7. Yes, that's the fifth term. Okay, so this looks right. This looks like it will it does recreate the sequence that we have. Okay. Do the same thing for the other two, please. Try to find the general term and then check your work. Make sure it's right. Go ahead. Okay, let's try the second one here in the middle. First, I see a negative, positive, negative, positive, negative pattern here. So let's take care of that part first. How can I build negative, positive, negative, positive, negative?
-1 power of n.
All right, -1 to the exponents n. So when n is 1, this is negative. When n is 2, it turns positive. When n is 3, it turns negative again. 4, positive. Okay, so that gives us the positive, negative parts. Now we can take care of the 5, 10, 15, 20, 25 part. What can we do for that?
Multiplied by 5n.
Times 5n. Okay, so we saw this in the earlier examples. So let's just focus on the 5n part. When n is 1, this is 5. When n is 2, this is 10. When n is 3, this is 15, 4, 20. Okay, looks like it's working out and it will rebuild the sequence. We could test this out. If you're testing your work, you don't need to like write it exactly like this. This is just a way of representing it. However you want to check your work, but do check for sure. Okay, this one is kind of the same as the 2 examples ago that we saw, so I won't rewrite it. It's basically the same thing. The next one here on the right, can someone give us an idea?
Negative n over n plus 1.
Negative n over n plus 1. Okay, so let's think about this. When when n is equal to 1, a1 would be negative n. So negative 1 over 1 plus 1. So negative 1 over 2. And for a2, when n is 2, that's negative 2 on the top, and 2 plus 1, negative 2 over 3. A3, negative 3 over 3 plus 1 is negative 3 over 4. And so, okay, we're seeing the pattern here. We've tested 3 of them, and we also can kind of just intuitively see, okay, it's going to work out. We can see how all these will work out. Negative 4 over 5, negative 5 over 6, negative 6 over 7, etc. So it works. Right. So identifying what a general term could be for a sequence. It could be anything. Any kind of math operation could be used to be building that sequence. The textbook has a good kind of random mix of questions in chapter 12.1 here, where they're just anything, like all kinds of different math tools and math properties and math operations are used to build sequences. And you just kind of have to look and see what's the pattern. Here's some random looking pattern, but what's the rule behind it? So it's good just kind of math problem solving or kind of math application, just how well can you recognize a pattern? So let's just try something here. This one. Their sequences can be built on all kinds of rules. There's lots of flexibility to them. Just trying to remember this. One, next one, 4. This is a very famous sequence in the math world. Does anyone see what's happening here? We can't define this with just a single general term. This is a different case. We'll have to talk about it a little differently.
Oh, I know. I think I see it. I think I see it.
Okay, tell me what you think.
So the second term is 1, right? It's like,
The second term is also 1. Yeah.
yeah, so it's like 1 plus nothing, right? And then the third term is 2, so it's 1 plus 1, the first term plus the second term.
Okay.
And then there's 5, right? That 5 is 3 plus 2.
Okay, so you're noticing what's happening here. It seems like we're taking the previous 2 terms and adding them together.
Yeah.
So the thing that's a little weird about this sequence compared to what we've seen so far, but this can happen, is we just define A1 is equal to 1 and A2 is equal to 1. We just say, like, there's no pattern behind it, just here's what they are. But then after that, an is equal to an minus 2. So the 2 terms ago plus an minus 1 term ago. So just basically each term is the sum of the previous 2. But then for the first 2, we have to just kind of spell out exactly what they are. So 1 plus 1 gives us 2, 1 plus 2 gives us 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc. This is a famous sequence in the math world. It's so famous that it even has its own name after the person who discovered it. Anyone know? Recognize this?
Is it like something series?
It starts with an F.
Oh, no, I don't know.
No, the it's an Italian name. Italian names are spelled weird. Fibonacci. I think someone can check my spelling on that. Fibonacci sequence. This one actually appears all over the natural world, like the pattern of a snail shell, or like all kinds of things where you would never expect it, but actually they follow this sequence, or this sequence does an excellent job of explaining or describing the pattern that we see in all kinds of things. That's why this one is very famous. Those weird math properties that we just notice in the natural world and places. So this is an example of a sequence as well. Again, they can be built on absolutely anything. In our class, we really care about the arithmetic and the geometric ones because they have tons of applications. But sequences can be all kinds of things. Okay, let's 8:30, we've gone for an hour. I'm gonna say this is a good time to take a break, and then we will come back and talk about the arithmetic sequences and series. Yeah, we can take a 10-minute break and we'll still have time to finish all of that. I have 8 more questions about the arithmetic sequences and series. So let's take a break. You can come back at 8:39, so 10 minutes from now. Stand up, stretch, get some water, go to the bathroom, whatever, and come back in 10 minutes. And since we're talking about this, if you have other questions about grade stuff, whatever, then you can ask, or if not, we will go on with the sequences stuff. Okay. All right, next part. So arithmetic sequences and series. So these are the ones where we learn these formulas. All right, we'll talk about the formulas on the next slide. That's where we'll need them. So first, you can look at this one and figure out is this an arithmetic sequence or not? And then second, you can look at this and use these parts to figure out the first 5 terms of the sequence. So go ahead, take a moment to try these out. Okay, let's take a look at these. The one on the left, how can we figure out if a sequence is arithmetic or not?
There should be a tangible difference. I mean, the same difference between numbers.
Okay, so common difference. So we just look at each pair and see if we have the same difference. So from 8 to 5, what's the difference?
-3.
-3. -3 because we're going down. It's always the second term minus the first term. So if we do it in that order, we do get a -3. 5 to 2, that's -3 again, and 2 to -1, -3, -3, -3. Okay, so it's a common difference. It's the same number each time. So yet, therefore, it is an arithmetic sequence. That is the definition. Must have the same difference between each of the terms. So yes, arithmetic. All right, the one on the right, how can we figure out the first 5 terms of this thing?
Add subtract 9 or add -9 to the number 5 times.
Okay, so what would the first term be?
5.
The one before that, bro.
Okay, so for the very first term, we don't apply D. It tells us right here, first term A1 is 14. So first term is 14. Then after that, we start applying D. So after that, we do 14 minus 9. 14 minus 9, which will give us 5 here. Okay, and then we do our -9 again. 5 minus 9 will give us -4. And then -4 minus 9 again will give us -13 and then -22. Okay, the other way that we could do this is we could figure out what the formula would be, make the general term, use our general term formula to make a general term, and then use that to calculate what each of them are. What is our formula for the general term of an arithmetic sequence?
An is equal to A1 plus n minus 1 multiplied by B.
Okay, so A1 plus n minus 1 times D. In today's class or yesterday's class, I explained the logic behind the formula, so I'll skip that part here. if we want to build the general term for this particular sequence, what can we do? So here's the formula, but I want to build an for this sequence here in particular. How can I do that using the formula?
Just substitute the values into the that equation.
Right, like, so I want a general term. I need A1. We have A1. I need D. We have D. So just put those numbers in. So an equals 14 plus n minus 1 times -9. And we'll just expand this and simplify it, and we'll get our term. So 14 plus n times -9. So this will become minus 9n. And then the next part, -1 times -9 will turn into positive 9 like this. And then 14 plus 9 will give us 25 minus 9. Sorry, not 25. 23 minus 9n. So there is our general term for this sequence. So we can kind of see the first term is 14, and then we're subtracting 9 each time. We see that if we go to the general term, we just sort of go one further. We don't really call it this, but we can imagine it's like an A0, sort of this imaginary first term, and then we subtract 9 from that to get our real first term, which is 14. If you want to think about it that way, that's what this number will be. So we could have gotten that without using the formula. Just say, okay, well, do the opposite of subtracting 9 one time, and that would have given us our 23 over here. And then that's what the constant will be for this term. That's kind of a shortcut, but if that doesn't make sense, then just use the formula, substitute in the numbers, and we'll get it. All right, next questions are going to use this formula here. So I hope you remember what that is, or you have that written down somewhere. All right. Okay, so they're written out as sentences like this in the textbook for whatever reason, but please read and then find the thing that it's telling you to find. All right, I will write out the formula one more time here at the bottom, in case you want to reference that as we're doing these. AN equals A1 plus n minus 1 times D. So the one on the left, we'll kind of figure out the parts that we are given here. So what are we told in the question? What information do they give us?
A1 and D.
A1 and D. A1, first term is 11. D is -6. And what are we looking for?
A16.
Okay, so A16, 16th term. And that's telling us, well, we want when n is equal to 16. So, okay, so n is 16. A16 is what? If you look at the formula, we have all the parts that we need right there. So A16 is equal to 11 plus n minus 1, 16 minus 1, 15 times D, which is -6. So 11 plus 15 times -6. What's that?
-90.
-90. So 11 minus 90, and that's going to turn into -79. So there we go. Just look at the information we're given. In this case, just very directly, we can use our formula. All right. So the next one on the right's a little different. What information were we given?
A3.
Okay, tell me what the thing is and tell me what it's equal to.
We are given
A-
A3.
Okay, so given A3. So A3 is 19. Have to make sure we read this carefully. Third term is 19. Here on the left, it was the first term, but here's the third term. What else are we given?
D is 5.
Okay, D5 and
We can find the first form according to that. A1.
we can. First, let's see like what else we're given here.
N.
Okay, so we're given n. We want our n is 11, and we are being asked to find A11. And also they want the general term. So AN is something. Okay. So it was pretty easy to use this formula on the one on the left because we were given A1, but here we're given A3. So what can we do with this?
Make a system of equations.
We could. I think it's possible to use A3 to find A1, and then we can use A1 with this formula down at the bottom here.
We can subtract 5
yes.
from 19 twice, 2 times.
Okay. So, and so 5, so A3, how can I write this? So something, 19, something. But we know that the D value is 5. So each time we're doing +5, +5. So we can just kind of undo that operation. So -5 would give us 14, -5 again would give us 9. So that's one way of thinking about it. So 9, that's A1. A1 is equal to 9. Or we can just use our formula, this formula down here. We can just sort of use it twice. First for A3. So A3 is 19. So therefore 19 is equal to mystery A1 plus n, which we know for this one with A3, then that's 3. So 3 minus 1 gives us 2. And then we know our d value, that's 5. So if we work this out, it would be 19 minus 10 equals A1. 19 minus 10, 19 minus 5 2 times, 19 minus 5 2 times. It's the exact same thing. We can do it with the formula, or we can just kind of think our way through it by writing out the numbers, but it's the exact same math. So this also gives us A1 is equal to 9 here. So we can use that formula. I'll erase this. And right, so A1 is equal to 9. And now that we have A1, we can just use this formula again to get A11. I always forget to turn that thing off. 1 second. There. Okay. So A1 is equal to 9, and then A11 therefore is 9. A1, 9 plus n minus 1. So 11 minus 1, 10 times our d value, which is 5. So 9 plus 50, 59. So there is our A11 value. And we were asked to do one more thing here to find the general term. How can we do that?
Substitute the values in.
Yeah, it's the exact same thing that we did before. We just take our values for A1 and D, and we'll get a term for our AN in terms of n. So A1, what did we say? A1 is 9 plus 1n minus 1 times 5. So 9 plus 5n minus 5. So it's an ugly looking 9. Let's try that again. And that's 4 plus, or let's write this the other way, 5n plus 4. Okay, there's our general term. There's A11. We found both of the things. We use this formula that we had here 3 times to figure out all this information, but still the same formula. If you have all the parts but one, you can just put them in the formula and figure it out. All right, let's do our 2 more sets of questions. The next one is going to be the one with the system of equations. Just give people a moment. They're writing. Okay, so next pair of questions here. So we want the general term for each of these, and we're just given some kind of random term somewhere in the middle of the sequence. Let's do the one on the left together. We had an example like this in class, but let's just do it together anyways, and then I'll let you do the one on the right. So on the left, what are we going to do to solve this?
Systems of equation.
Okay, tell me specifically, what's the equation?
The first one, 14 equals to A1 plus D. Second
14
one,
equals A1 plus D. Okay, so I'll just I'll write a tiny bit more here. So plus, this is for A2. So for A2, just using that same formula for the general term, 14 plus equals A1 plus N minus 1, but so it's 2 minus 1 times D, but of course, 2 minus 1, that's just 1. So A1 plus D. Okay, what's our other one?
47 equals to A1 plus 12D.
Okay, so for A13, exact same thing. 47 equals A1 plus 13 minus 1, 12 D. Okay, so we have equation 1 and we have equation 2, and we just need to solve 2 equations, 2 unknowns. What's your choice here? Substitution or elimination?
Elimination.
Elimination, okay. What are we doing for elimination?
Eliminate A1.
Okay, so with the equations, do we have to multiply by anything?
No.
No. So we're just subtracting. It doesn't matter what order we subtract in. So let's just do equation 1, equation 2, and subtract. So 14 equals A1 plus D. 47 equals A1 plus 12D, and A1s disappear. D minus 12D, so that's negative 11D. What are we going to get on the left here?
Negative 33.
Right, negative 33. So negative 33, negative 11, and that's just turning into 3, positive 3. Okay, there's our D value. What are we going to do with this?
We can find A1 using that.
Okay,
Using-
so, all right, so we have 2 equations and we found one of the unknowns. So we just substitute this back into either one of the originals. Equation 1 looks like it's really easy to work with. So D into equation 1, which would give us 14 equals A1 plus 3. So A1 is equal to 11. All right, there's our A1, there's our D. And now what are we going to do?
Use both values to make the general term.
General term. So general term formula, once again here, AN is equal to A1 plus N minus 1. D, substitute in these numbers, AN is equal to 11 plus N minus 1, and D is 3. So we'll just skip some stuff here. 11 minus 3, that's 8, and 3N, so 3N plus 8 is our general term. So simple system of equations to solve this. We just use our general term formula twice and then our, or sorry, 3 times, one more time to get the actual general term here. Go ahead, do the same thing on the right, please. Okay, let's try here. What are the two equations that we are going to have here? We have a 4th term and a 15th term. What are each of these equations?
-6 equals a1 plus 3d.
A1 plus 3d, okay, and
27 equals a1 plus 14d.
A1 plus 14d. So these are pretty simple forms here. We're just kind of keep seeing the same patterns. Whatever the term itself is, it's going to be on the left. And then we're multiplying d by 1 minus whatever n is, but they're all going to look really, really similar to this. Okay, and then substitution, let's just do elimination. Let's be extra lazy here and not rewrite these. And let's call this equation 1, equation 2, and we're just going to subtract and then see what we get. So on the left, -6 minus 27, what do we get?
-33.
-33. Again, like on the other question. So coincidence. A1's disappearing, and what's our other term going to be?
-11d.
-11d. Complete coincidence. Maybe I should have chosen a different question just so we don't get confused and think this is always going to happen. But d happens to be 3 here, okay? And we'll take this and let's say d into equation 1. So -6 is equal to a1 plus 3 times 3 here. All right, so a1 is equal to
-15.
-15, so -6. And then this is 9 here, so -6 minus 9, -15. Okay, so we want the general term, so we don't need an n. It's just going to be, the n will stay there. So an is equal to a1, -15 plus n minus 1 times our d value, which is 3. Okay, so the n is going to be 3n. And then we have -15, and we will be subtracting 3, -1 times 3, so -18. There's the general term, and of course we can use that to find any term in the sequence. Okay, that's how we do these. So you can get a term that's anywhere in the middle of the equation, and you can still anywhere in the middle of the sequence, and just do some system of equation stuff to figure out what the rest of the pattern is. All right, I will just give another moment and then erase. And then the last two with partial sums. You can start trying to remember what the formula is for a partial sum for an arithmetic sequence. Okay. So last ones here. So sum, sum again means we are adding up all of the parts. So that means that we're going to take this thing and imagine we have a plus sign between all of these. So -17 plus -15 plus -13 plus -11 plus ... for 30 terms, up to whatever those would be. What is the formula for the partial sum of an arithmetic sequence?
Sn is equal to n over 2 multiplied by 2a1
Okay, 2a1
plus n minus 1d.
n minus 1d. The other way of writing this is n over 2 times a1 plus a n. If we just take the an term and use our general term formula and expand that, then we will get to exactly what we have in the second version here, but they are saying the same thing. Also in today's class or yesterday's class, depending on your section, I talked about the kind of the rationale and the theory and the logic behind the formula. I won't repeat that here. It's not too complicated, but there is a very good reason for this formula. Okay, so let's see if we can do this. On the one on the left here, Q11, let's see what we need. A1. Yes, we have A1. I'm just going to erase this for space. A1 is equal to -17. We have that. We want the first 30 terms. So n is 30. And our Sn is the thing we're trying to find. Sn. Okay. Are we ready to use the formula?
We need d, but
Okay, so we need
Yeah.
D. It's not going to be hard to find given what we have here, but we do need that. So our D term, what is that?
2.
2.
2. So just positive 2 plus 2 plus 2 plus 2 plus 2. We can just look at the sequence and see it directly there. 2. Okay. So now we're ready to use the formula. Sn equals, not Sn, S30 equals 30 over 2, 2 times a -17 plus n minus 1, 29 times d, which is 2. Okay, and we just want to solve this. 15 and -34 plus here 29 times 2, 58, 15 times -34 plus 58. What is that?
24.
24. Okay, so 15 times 24. What is that?
360.
360. 24 times 1.5. This might be easy enough to do in our heads. That's going to be 36. And then we just add a 0 to the end of that. 360. Okay. There's our answer. Partial sum for that sequence here. We could find the general term. We weren't asked to do that. Just we want that partial sum. Please do the same thing for the one on the right here. Okay, that was 2 minutes. So let's try. We have two versions of the formula at the bottom. With the information that we've been given on this question, which one seems like it'll be easier to use? It's not a huge difference, but still. Which one?
The first one.
The first one. We're given a general term formula, and we want the sum of the first 50 terms. Let's write that. And as 50 is what we're being asked to find, but we have n equals 50 here. So we just use this general term to find a1 and a n, and then we're ready for the first one here. We can also see, okay, d is going to be -3. We can just kind of know what that's going to be by looking at the coefficient of the n term, but let's just keep things real safe and predictable here. So a1 is going to be equal to -3 times 1 plus 5. Okay, so -3 plus 5 to a 50 is going to be -3 times 50 plus 5. -3 times 50, -150 plus 5, -145. And then we're ready for the formula. So S50 equals 50 over 2. And A1 is 2. A50 is plus -145. And simplify 25 times -143. And then we figure that out, whatever that ends up being here. Just my personality, I would want to kind of split up the 143 into like 140 and 3 or something, but whatever way we want to do it would be fine. Yeah, that would work. That wouldn't be too bad. 250, yeah. But we can also just use our long multiplication, 1, 4, 3, 25, 5, 1, and 1, 2, 7, plus 6, 8, 1, and 5, 7, 5, carry the 1. Oh, sorry, that's not a 1. That's a 2. And 5, carry the 1, and 3, and it's -3, 5, 7, 5. Okay, there is our sum. So as I mentioned in class, being able to do long multiplication quickly like this will be very useful. So good thing to practice if you're the always go to a calculator type person. Start practicing actually writing out the multiplication, because as I've stated before, our exams are technology free. Well, computer and everything, yes, we have to use it, but not able to use calculators. Okay, that's the last one that I had for us. Does anyone have questions about this? What we did here? Nope. Okay. Well, so two formulas for this general term and the partial sum for arithmetic sequences. We can use those anywhere or all kinds of places to solve a bunch of different types of questions, but it really just is the same two formulas over and over and just slightly different orders or slightly different methods. All right, if that's that, then just do a quick wrap up. We got through all the questions and we're just about at our time. So some exponent rules. I didn't do kind of the simpler version of these. The questions we did sort of combined a bunch of those rules. So make sure you practice questions like these ones, and you can use multiple rules together and see how they connect with each other and everything. With kind of roots like fractional exponents or the square roots or square roots, cube roots, etc. Being able to work with those. Chapter 8.3, there's also chapter 8.2, which is more just about written as roots. 8.3 has them written as fractional exponents. It's the exact same math, it just looks a little different, but doing some practice with both of those would probably be good. Sequence general skills, so just being able to recognize any kind of sequence, which again could be built on any kind of thing, any sort of math, whatever. We will be spending most of our time talking about arithmetic and then geometric sequences built on addition and multiplication, but they could really be absolutely anything. There's millions of known sequences, all with all kinds of weird properties defining how you get the terms. But focus on arithmetic, geometric, those two formulas, we can do a lot with them. All right, done. If you have questions, hang around and ask. Otherwise, I will see you guys next week for our next class.
Thank you, Professor.
Bye.
Professor.
Thank you,
Thank
Professor.
you. Goodbye.
Goodbye.
Thank you, Mr. Prof.